It's hardly a secret that our sun is ultimately the driving force behind the planet's weather. The sun, a large radiant object, heats the Earth, but because the Earth rotates and has mountains and valleys and oceans and cities, the planet heats unevenly. Uneven heating results in weather, a constant battle the planet wages trying to regulate its differences. But what about weather outside the planet? Now, most people think that space is completely void, and for the most part that's the case. But what if I told you that there's an entire field of study dedicated to space weather? Let's explore some of the topics in that field today. First, it helps to understand exactly what the sun is made of. 93 million miles away from us, we find a glowing ball composed mostly of hydrogen and helium. The sun's mass is over 330,000 times greater than Earth's. An equivalent comparison would be a 150-pound person versus a 1-carat diamond. The sun is constantly undergoing a violent molecular process called fusion. Two hydrogen atoms are smashed together, forming helium ions and eventually neutral helium. This process is quite explosive and results in lots of energy being given off by the sun, some of which winds up heating our planet. The rest travels infinite distances through space, hence the reason we can see other stars in our night sky. In recent decades, several nations have launched satellites with the intent of learning more about the sun. One of the most powerful satellites was launched by NASA and is monitored jointly with the Space Weather Prediction Center. Dubbed the Solar Dynamics Observatory, or SDO, this satellite is similar to the GOES satellites we talk about frequently on this show, in that it is a geostationary satellite that images the sun using several different wavelengths, or bands. By imaging the sun using all of these different wavelengths, over 25 of them in total, we can observe all sorts of phenomena. One of these is solar flares. These appear as bright flashes of light on the sun's surface, caused by intense bursts of electromagnetic radiation leaving the sun in the form of photons. When such an abnormally high concentration of photons arrives at the Earth, the ionosphere becomes highly charged, particularly the lower D and E layers. Ionization of these layers can effectively black out transglobal radio communications that don't rely on satellites. Some of the strongest solar flares in recent years occurred in September 2017, when X8.2 and X9.3 class flares were observed by the SDO. X-class flares are the most powerful flares our sun can emit. Degradation occurred across amateur radio bands below 30 MHz. It was very difficult to make contacts outside North America. A flare in 2000 was also responsible for triggering radiation alarms on the then-new International Space Station. Astronauts and cosmonauts had to work out of a specially designed radiation shelter for about 12 hours until the storm subsided. Closely related to solar flares are coronal mass ejections, or CMEs. These appear on stars, including our sun, as clouds of superheated plasma departing a star quickly. Electromagnetic radiation usually accompanies the fast-moving cloud. Check out this video from NASA's Goddard Space Flight Center showing what a CME looks like. The particles from this CME in August 2012 raced away from the sun at 900 miles per second. That's the distance from Philadelphia to Memphis. If a powerful CME is directed at the Earth, there could be several consequences. Perhaps the most significant is the disruption of satellites. The 2,000 active satellites that orbit the Earth are responsible for everything from GPS to television to global communications. If they are exposed to unusually high amounts of electromagnetic radiation, their solar panels and onboard computers could be disrupted, thus blacking out some services. This happened in 2017 when a flare in CME disrupted GPS satellites for about a week, causing some pinpointed locations to be several miles off. There are a few other big topics in space weather, most of which we don't have time to cover today, but one of them could have impacts on the planet's surface. You've probably heard of supernova, the colorful clouds that appear in space when a star dies and explodes. But when that explosion is over and the star's remnants implode, the gravitational attraction is so strong that massive amounts of all sorts of radiation are emitted. Scientists currently do not know of a phenomenon that emits more radiation than this. These radiation bursts are called gamma ray bursts, or GRBs. Ranging in duration from a few milliseconds to a couple of hours, these extrasolar events pose a direct threat to organic life. Most GRBs occur millions to billions of light years away from the Earth and simply appear briefly as faint spots in the night sky, invisible to the naked eye. However, if one were to occur close to Earth, the burst of gamma radiation could harm the ozone layer, which has the job of shielding us from much of the sun's harmful UV radiation. A strong GRB could cause increased UV levels at the surface for several years, harming both plants and animals. Increased levels of smog and a higher frequency of acid rain could also occur, though scientists aren't yet sure to what extent. The only GRB candidate near Earth, a star about 8,000 light years away, isn't due to cause a burst for tens of thousands of years. So in the meantime, we can simply enjoy the visuals that our sun and other stars have to offer to scientists and to stargazers, knowing that Earth isn't the only place with a wide variety of weather phenomena. For Weather World, I'm Christopher Tate.